Right now, as you listen to these words, something impossibly old is passing through our solar system. Something that has been traveling through the darkness of space since before Earth existed, since before the sun ignited, since before anything you know was born. On July 1st, 2025, at the Atlas Telescope facility in Chile's Rio Hurtado Valley, an automated survey captured something that shouldn't exist, an object moving at 245,000 kilometers per hour. Too fast, wrong trajectory. When astronomers traced its path backward through space, they discovered it hadn't come from the outer solar system or the Kuiper belt, or even the distant Oort cloud. It came from another star. But here's where the mystery deepens. This visitor, designated 3I Atlas, the third confirmed interstellar object in human history, reached its closest point to our sun on October 29, 2025, just before Halloween, hidden from Earth's view behind the solar glare. And its trajectory. It passes suspiciously close to Venus, Mars, and Jupiter, a path that seems almost deliberate. Why would an object estimated to be 7 to 14 billion years old arrive now taking a route through the inner solar system that brings it near multiple planets? Why did we almost miss it entirely hidden, as it was against the dense star fields of the galactic center? And what does this ancient cosmic messenger tell us about the universe we inhabit? Tonight, we're going to explore one of the most profound scientific events of our lifetime. We'll examine the hard data from NASA ESA, the Hubble Space Telescope, and the James Webb Space Telescope. We'll hear from the astronomers racing to study this object before it vanishes forever. We'll consider three distinct hypotheses about what 3I Atlas truly is, from the mainstream scientific explanation to edge-case natural phenomena to bold speculation that challenges everything we think we know. The stakes couldn't be higher, because every interstellar visitor carries information from beyond our cosmic neighborhood. Each one is a message in a bottle thrown across the galaxy, and this message, it's written in ice that formed when the universe was young. The terrifying truth isn't about danger to Earth. The terrifying truth is what 3I Atlas tells us about time, about age, about the universe's patient memory, and about how much we still don't understand about the cosmic ocean we're swimming in. So settle in, turn down the lights, and let's follow this ancient wanderer on its journey through our brief moment of sunshine. The night of July 1st, 2025 began like thousands before it at the Atlas Telescope facility in Chile. Atlas, the asteroid terrestrial impact. Last Alert System is designed for one primary purpose: to scan the sky, repeatedly looking for anything that moves, anything that changes, anything that appears where nothing existed before. Think of Atlas as a cosmic security camera taking picture after picture of the same patches of sky. When something moves between frames, software flags it automatically. Most of these detections are mundane, known asteroids on their predictable orbits, satellites, cosmic rays hitting the detector. The system processes thousands of candidate objects every night, filtering out the noise to find genuine discoveries. But on this particular night, one detection refused to fit the patterns. The object was moving too fast for a typical asteroid. Its trajectory suggested extreme speed relative to the solar system. When astronomers plotted its path, something impossible emerged. The orbit wasn't elliptical. It wasn't even parabolic. It was hyperbolic, meaning this object was moving so fast that the sun's gravity couldn't capture it. It would swing past once and vanish forever into the depths of space. The initial observations were tentative, possibly an error, possibly a glitch. But within hours, the Atlas team sent their data to the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries. The message was carefully worded, but urgent. We have something unusual. We need confirmation. And confirmation came quickly. Astronomers began searching through archival data from other sky surveys, looking for earlier images of this mystery object. What they found was remarkable. The Zwicky Transient Facility at Palomar Observatory had captured it on June 28th and 29th. Then searches uncovered ZTF observations from June 14th through 21st. Atlas itself had pre-discovery images from June 5th through 29th. This object had been crossing our sky for nearly a month before anyone noticed it. But why? Why did an object moving at such extraordinary speeds escape detection for so long? The answer lies in timing and geometry. During late June 2025, from Earth's perspective, this object was passing in front of the galactic center, that dense, brilliant core of the Milky Way where millions of stars cluster together. It's like trying to spot a single firefly against the blazing lights of a city skyline. The object was there documented in images but invisible in the overwhelming stellar background. Only when it moved away from that confusion of starlight did automated detection systems flag it as something new. By July 2nd, astronomers had accumulated enough observations to calculate a preliminary orbit. The numbers were staggering. The orbital eccentricity, a parameter that describes the shape of an orbit, came back at 6.137 plus or minus 0.006. For context, a perfect circle has an eccentricity of 0. Earth's nearly circular orbit has an eccentricity of 0.017. Even the most elongated comet orbits in our solar system rarely exceed eccentricities of 1.0. An eccentricity of 6.137 is extreme. It means the trajectory is essentially a straight line barely curved by the sun's immense gravitational pull. This wasn't just unusual. This was interstellar. But there was another question to answer. Was this object an asteroid or a comet? The distinction matters enormously to scientists. Asteroids are rocky or metallic bodies, leftover building blocks from planetary formation. Comets are ice and dust conglomerates, preserved samples of the volatile materials that existed in the outer regions of a planetary system. Initial observations were ambiguous. The object appeared point-like, without the characteristic fuzzy coma that surrounds active comets. Several astronomers, including veteran comet observer Alan Hale, reported seeing no cometary features at all. Then, on July 2nd, everything changed. 3 separate observatories, the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope on Mauna Kea, all reported the same finding, a marginal coma with a potential tail-like elongation, approximately 3 arc-seconds in length. The object was active. It was outgassing. It was a comet. That same day, the Minor Planet Center made it official. They assigned the designation 3I Atlas, the 3I signifying the third confirmed interstellar object in history, and Atlas, crediting the survey that discovered it. They also gave it the non-periodic comet designation, C 2025 N1. By the time the announcement was made, 122 observations from 31 different observatories had been collected and analyzed. Astronomers David Jewett and Jane Liu, using the Nordic Optical Telescope, confirmed on July 2nd that 3I Atlas was clearly active with a diffuse appearance. The mystery object had revealed its nature. Not a barren rock tumbling through space, but an icy body awakening as sunlight warmed its ancient surface. The universe had sent us a comet that formed around another star. A comet that might be twice as old as our entire solar system. And humanity had exactly 4 months to study it before perihelion, before it passed closest to the sun, and began its exit from our cosmic neighborhood forever. The race was on. But first, scientists needed to understand what they were looking at. Where had this visitor come from? What was it made of, and most importantly, what could it tell us about the countless other planetary systems scattered across the galaxy? These questions would require the most powerful telescopes humanity has ever built. And what they discovered would challenge our understanding of how comets form, how solar systems evolve, and how common or rare the conditions for life might be throughout the universe. But we're getting ahead of ourselves. Before we can appreciate the mystery, we need context. We need to understand what makes an object interstellar in the first place, and we need to know about the two visitors that came before. Imagine standing on Earth and throwing a ball straight up. If you throw it gently, it rises and falls back to your hand. Throw it harder, and it rises higher before gravity pulls it back. But if you could throw that ball at 11.2 kilometers per second, Earth's escape velocity, it would never return. It would break free of Earth's gravitational embrace and sail off into space. This is the fundamental principle that defines interstellar objects. Every object in orbit around the Sun follows a path determined by its speed and distance from our star. Most objects, planets, asteroids, comets, move in elliptical orbits, endlessly circling the Sun. Their orbital eccentricity, that measure of an orbit's shape, is less than 1.0. These objects are gravitationally bound to our solar system. They're family. But when an object enters our solar system from interstellar space, it arrives with such tremendous velocity that the Sun's gravity can't capture it. Its eccentricity exceeds 1.0, creating a hyperbolic trajectory. The object swings past the Sun just once, and then escapes back into the galactic darkness. These visitors aren't bound to us, they're just passing through. Before 2017, this concept was purely theoretical. Astronomers knew such objects must exist. After all, planetary systems eject comets and asteroids all the time during their formation and evolution. These cast-off bodies must wander through interstellar space. Logic demanded it. But despite decades of sky surveys, despite millions of observations, despite thousands of discovered asteroids and comets, not a single interstellar visitor had been confirmed. Then came October 19, 2017. The Pan-STARRS telescope in Hawaii detected something impossible. The object was moving at 26 kilometers per second relative to the Sun, fast enough to escape the solar system entirely. Its trajectory was hyperbolic. And most strangely, it was tumbling end over end rapidly, causing its brightness to vary dramatically as different surfaces caught and reflected sunlight. Initial observations suggested it was extremely elongated, perhaps 10 times longer than it was wide. Some astronomers described it as cigar-shaped, though later analysis suggested it might be more disc-like. It was small, probably no more than a few hundred meters across, and crucially, it showed no signs of cometary activity. No coma, no tail, no outgassing. The object was designated 1I Oumuamua, combining 1I for first interstellar with the Hawaiian word meaning scout, or messenger from afar arriving first. Oumuamua was unlike anything in our solar system. Its unusual shape, its lack of cometary activity despite passing close to the Sun, and most puzzling, a slight, unexplained acceleration as it departed the solar system. This tiny boost in speed couldn't be explained by gravitational interactions alone. Something was pushing it. Some scientists suggested asymmetric outgassing of volatiles, too faint to detect visually. Others proposed solar radiation pressure acting on an unusually low-density object. And yes, a few researchers, most notably Avi Loeb of Harvard, speculated that Oumuamua might be artificial, perhaps a light sail from another civilization. The astronomical community largely rejected the artificial hypothesis, but the mystery remained. Oumuamua defied easy categorization. And by the time its oddities were fully catalogued, it was already too far away for detailed follow-up observations. Humanity's first confirmed interstellar visitor had come and gone, leaving more questions than answers.
But we wouldn't have to wait long for the second visitor. On August 30th, 2019, amateur astronomer Gennady Borisov, using a telescope he built himself in Crimea, spotted a comet with an unusual orbit. Follow-up observations quickly confirmed what Borisov suspected: the object was moving on a hyperbolic trajectory. Another interstellar visitor. This time, astronomers were ready. The object designated 2I Borisov was discovered much farther from the Sun than Oumuamua had been, providing months of observation time before and after perihelion. Every major telescope on Earth and in space was turned toward this cosmic interloper, and 2I Borisov. It looked normal, beautifully, wonderfully normal. It was clearly a comet with a bright coma and distinct tail. Spectroscopic observations revealed it was rich in carbon monoxide, unusual for solar system comets, but not impossibly so. It broke into at least 2 fragments, just as comets often do when heated by the sun.
Its nucleus was estimated at roughly 1 kilometer across. In almost every way, 2I Borisov behaved like a typical comet from our outer solar system, just one that happened to come from somewhere else. It was familiar enough to be comforting, yet different enough to be scientifically valuable. The discovery of 2I Borisov confirmed what Oumuamua had suggested: interstellar objects regularly pass through our solar system. We simply hadn't been looking carefully enough to find them. Statistical models based on these 2 discoveries suggest that at any given moment there might be one interstellar object closer to the Sun than Neptune. Over the course of a year, dozens might pass through the inner solar system. Over millennia, millions have traversed this space, unseen and unsuspected silent messengers carrying information from across the galaxy. But here's the profound truth: we can only detect the largest and brightest of these visitors. Smaller objects, anything below a few hundred meters across, slip past us unnoticed. Our sky surveys are improving, but they're still limited by telescope-sized detector sensitivity and the vast volume of space that must be monitored. Every confirmed interstellar object is therefore precious beyond measure. Each one represents a physical sample from another star system, something we can observe, measure, and analyze without having to travel light years from home. Each one tells us about the materials, conditions, and processes that existed where it formed potentially billions of years ago. Oumuamua taught us that interstellar objects might be stranger than we expected. 2I Borisov reassured us that some would be familiar, and now with 3I Atlas we're learning that every visitor brings its own unique story. 3 confirmed interstellar objects in 8 years. 3 completely different profiles. 3 windows into 3 separate corners of the galaxy. But 3I Atlas isn't just another data point. It's the most extreme case yet, the fastest, the oldest, the most chemically unusual, and it's following a path through our solar system that some find troubling. Let's talk about speed. Real speed, cosmic speed. When you drive a car at highway speed, you're moving at roughly 30 meters per second. That feels fast because you can see the landscape rushing past. A commercial jet cruises at about 250 meters per second, fast enough that the ground below becomes an abstract blur. Now scale up. Earth orbits the Sun at 30 kilometers per second. That's 30,000 meters every second, covering nearly 1 million kilometers every day. At that speed, you could circle Earth's equator in about 23 minutes. When 3I Atlas was discovered on July 1, 2025, it was traveling at approximately 61 kilometers per second relative to the Sun. That's more than twice Earth's orbital speed. That's 220,000 kilometers per hour. At that velocity, you could travel from Earth to the Moon in less than 2 hours. But here's what makes 3I Atlas truly extraordinary: as it approached the Sun, it accelerated. By the time it reached perihelion on October 29, 2025, it was moving at 68 kilometers per second. That's 245,000 kilometers per hour. This isn't unusual. Physics objects naturally speed up as they fall toward the Sun, converting gravitational potential energy into kinetic energy. What's unusual is how extreme that final velocity becomes when you start with so much initial speed. The orbital eccentricity of 3I Atlas is 6.137 plus or minus 0.006. This is the highest eccentricity of any interstellar object yet discovered. Oumuamua's eccentricity was 1.2. 2I Borisov's was 3.4. 3I Atlas has nearly doubled the previous record. What does this extreme eccentricity mean in practical terms? It means the trajectory through our solar system appears almost straight. Yes, the Sun's gravity bends the path slightly, creating a gentle hyperbola, but the deflection is minimal. 3I Atlas is moving so fast that even our star's immense gravitational pull barely nudges it off course. Now let's trace that path backward through time and space. By analyzing 3I Atlas's velocity and direction, astronomers can decompose its motion into three components using the galactic coordinate system. The U component measures velocity toward or away from the galactic center. The IV component measures motion in the direction of galactic rotation, and the W component measures velocity perpendicular to the galactic plane, up or down relative to the Milky Way's disk. When 3I Atlas entered our solar system, it was moving away from the galactic center with a U velocity of negative 51.0 kilometers per second, and it was moving upward through the galactic plane with a W velocity of positive 18.5 kilometers per second. That W velocity is crucial. It's quite high compared to most stars and other interstellar objects in our neighborhood. Objects with high perpendicular velocities follow tilted orbits around the Milky Way's center, oscillating up and down through the galactic plane like a sine wave. This motion is characteristic of either the thin disk or thick disk populations of stars. The thick disk is fascinating. It consists primarily of older stars that formed when the galaxy was younger and had different chemical compositions. The thick disk is a population of galactic senior citizens, and 3I Atlas with its high W velocity likely belongs to that ancient demographic. Based on typical ages for thick disk stars, researchers estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old. Let that sink in for a moment. Our Sun is 4.6 billion years old. Earth is 4.5 billion years old.
Every living thing on this planet, every mountain, every ocean, every human civilization, all of it, has existed within a time span shorter than 3I Atlas's journey through space. This comet may have formed when the universe itself was less than half its current age. But here's where the trajectory becomes even more intriguing, the path 3I Atlas takes through our solar system. On October 3, 2025, it passed within 30 million kilometers of Mars, its closest approach to any planet during this transit. Less than a month later, on October 29th, it reached perihelion at a distance of 1.36 astronomical units from the Sun, placing it squarely between the orbits of Earth and Mars. Then, on November 3, 2025, just 5 days after perihelion, it will pass within 97 million kilometers of Venus. On December 19, 2025, 6 days before Christmas, it reaches its closest approach to Earth. 267 million kilometers. That's safely distant about
8 times the Earth-Sun distance, but still close enough for detailed observations. Finally, on March 16, 2026, 3I Atlas will arrive at its closest distance from Jupiter, 54 million kilometers. 4 planets, 4 relatively close approaches, all within 7 months. Is this unusual? Yes and no. Any object passing through the inner solar system will necessarily pass by the planets that inhabit this region. That's simple geometry. The planets aren't randomly scattered. They're confined to a relatively narrow plane called the ecliptic, and 3I Atlas's trajectory lies close to the ecliptic plane, so planetary encounters are inevitable. But the timing feels convenient. Perihelion occurring exactly when Earth can't observe it directly, because it's behind the Sun. The sequence of planetary flybys providing multiple observation windows. The path that carries it past 4 major worlds. Harvard astrophysicist Avi Loeb has noted this trajectory with particular interest. In a paper titled, "Is the Interstellar Object 3I Atlas Alien Technology?" Loeb writes, "The fundamental question is whether 3I Atlas is a Trojan horse with the external appearance of a natural comet, but carrying a potential threat in its interior." He points out that perihelion, the closest point to the Sun, would be the optimal time for any spacecraft to either accelerate or decelerate, using the Sun's gravity for assistance. It's also the ideal moment to release smaller probes that could then maneuver toward planets. And we couldn't watch. We were blind during the most critical moment. Now, to be absolutely clear, Loeb's hypothesis represents a tiny minority view in the astronomical community. The vast majority of scientists see no evidence whatsoever for artificial origin. The trajectory, while interesting, can be completely explained by natural gravitational dynamics. But the question lingers in the mind. We'll explore that speculation more deeply later.
For now, the key point is this. 3i Atlas is following a path through our solar system that takes it past multiple planets, reaches perihelion at a time when Earth's observations are blocked, and does so at a speed that makes capture impossible. Whether by design or cosmic coincidence, this ancient visitor is here for a brief moment, offering us a glimpse of something impossibly old, and then departing forever. Our window of opportunity is closing. But before it does, we need to understand what this object is made of, because the chemistry of 3i Atlas is perhaps the most surprising aspect of all, and it starts with ice, very, very cold ice. When you hear the word comet, what image comes to mind? Perhaps a bright streak across the night sky, a glowing head with a magnificent tail streaming behind it. These are the spectacular visitors we remember. Comet Hale-Bopp in 1997, Comet Hyakutake in 1996, the great comets of centuries past. But what creates that beauty? What causes a comet to shine? The answer lies in ice. Not the ice in your freezer, but ancient ice, frozen water. Frozen carbon dioxide, frozen methane, frozen ammonia, all mixed together with dust and rocky particles. This material has been preserved at temperatures close to absolute zero for billions of years, unchanged since the comet's formation. As a comet approaches the sun, solar radiation begins to warm its surface. The frozen volatiles don't melt, they sublimate, transforming directly from solid to gas without passing through a liquid phase. This outgassing carries dust particles with it, creating a cloud called the coma that surrounds the nucleus. Solar wind and radiation pressure then push this material away from the comet, forming the characteristic tails. Different ices sublimate at different temperatures. Water ice begins significant sublimation at temperatures above about -120 degrees Celsius. Carbon dioxide ice-dry ice sublimates at much lower temperatures, around -78 degrees Celsius at standard pressure, but even colder in the vacuum of space. This means carbon dioxide becomes active much farther from the sun than water ice does. A CO2-rich comet will start outgassing while still far from the sun, developing a coma long before a water-rich comet at the same distance would show activity. Keep this in mind, it becomes crucial. When 3i Atlas was first detected on July 1, 2025, the observations were ambiguous about its nature. It appeared as a point source of light moving rapidly against the background stars. No obvious coma, no visible tail. Several experienced observers reported seeing nothing that suggested cometary activity. Then came July 2nd. 3 separate observatories using different telescopes, different detectors, different analysis techniques, all reported the same, finding a marginal coma with a faint tail-like elongation, approximately 3 arcseconds in angular size. The object was active. It was a comet. But the distance from the sun at that moment was still quite substantial. For a typical solar system comet dominated by water ice, significant activity wouldn't be expected at that distance. The fact that 3i Atlas was already outgassing suggested something unusual about its composition. The world's most powerful telescopes were immediately redirected toward this cosmic interloper. On July 21, 2025, the Hubble Space Telescope captured detailed images of 3i Atlas from a distance of 277 million miles. Hubble's sharp vision revealed a teardrop-shaped cocoon of dust emanating from the comet's nucleus. Because Hubble was tracking the comet's rapid motion, the background stars appeared as streaks in the exposure, a stunning visual reminder that we were observing something racing through our solar system at extraordinary speed.
Hubble's observations also allowed astronomers to constrain the size of the nucleus. As of August 20th, 2025, the data indicated that the comet's diameter was not less than 440 meters and not greater than 5.6 kilometers. That's a wide range, but given the difficulty of separating the faint nucleus from the bright coma, even these broad limits were valuable. But size wasn't the most important question. Scientists wanted to know, what is this thing made of? Enter the James Webb Space Telescope. On August 6th, 2025, JWST pointed its near-infrared spectrograph instrument at 3I Atlas. Where Hubble had provided images, JWST would provide a chemical fingerprint. By analyzing the wavelengths of light absorbed or emitted by molecules in the comet's coma, scientists could identify the specific compounds present. The results were astonishing. 3I Atlas has a carbon dioxide to water ice ratio of approximately 8:1. For every one water molecule, there are 8 carbon dioxide molecules. To put this in perspective, most comets in our solar system have ratios closer to 1:1 or even water-dominated compositions. Some Oort cloud comets show elevated CO2 but nothing approaching an 8:1 ratio. This is among the highest CO2 to water ratios ever measured in any comet anywhere. Why does this matter? Because composition tells us where and how a comet formed. Water ice is relatively abundant in protoplanetary disks, the spinning clouds of gas and dust from which planetary systems form. Carbon dioxide is also present, but it's typically frozen onto dust grains in the coldest outer regions of these disks, far from the parent star, where temperatures drop to just a few dozen degrees above absolute zero. For 3I Atlas to have such extreme CO2 dominance, it must have formed in the outermost reaches of its birth system, where temperatures were so low that carbon dioxide could efficiently accrete, while water remained relatively scarce. Or perhaps the system's chemistry was fundamentally different from our own, producing a different balance of volatile materials during planet formation. This is profound. This tells us that the planetary system that created 3I Atlas was not like ours. The conditions, the temperature gradients, the chemical abundances, something was different. And that difference is preserved in this ancient ice, readable billions of years later. But there was another surprise waiting. NASA's Neil Gehrels Swift Observatory, equipped with its ultraviolet optical telescope, observed 3I Atlas during July and August 2025. Swift's ultraviolet capabilities allow it to detect hydroxyl OH molecules, a chemical signature of water vapor escaping from the comet. And there it was, a faint but unmistakable glow of hydroxyl surrounding the nucleus. Dennis Bodowitz, a professor of physics at Auburn University and lead researcher on the Swift observations, captured the significance perfectly. When we detect water, or even its faint ultraviolet echo, CH from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. Water, carbon dioxide, dust, the building blocks of worlds delivered from across the galaxy. But the chemical analysis wasn't finished. Spectroscopic observations also revealed unusual abundances of certain metals. Nickel appeared in higher concentrations than typically seen in solar system comets. Conversely, iron, which is usually abundant, seemed deficient. These metal abundances provide clues about the environment where 3I Atlas formed. The relative proportions of different elements reflect the composition of the molecular cloud that collapsed to form the comet's parent star. Each stellar nursery has a unique chemical fingerprint determined by what earlier generations of stars had synthesized and scattered into space through supernova and stellar winds. 3I Atlas is carrying a record of its birth environment, and that record is strikingly different from our own solar system's composition. Zexi Xing, a postdoctoral researcher working with the Swift team, put it this way: Oumuamua was dry, Borisov was rich in carbon monoxide, and now Atlas is giving up water at a distance where we didn't expect it. Each one is rewriting what we thought we knew about how planets and comets form around stars. Each interstellar visitor is unique. Each comes from a different place, formed under different conditions, carrying different information. The universe is not uniform. Planetary systems are not all variations on a single theme. They are diverse, creative, unexpected, and we're only beginning to sample that diversity. But there's something else about Three-Eye Atlas's chemistry that has raised questions. Something about when and where the outgassing began. Something that a few researchers find puzzling. The comet became active started showing a coma while still quite far from the sun, farther than would be expected even for a CO2-rich object under normal conditions. This early activation suggests either an extremely sensitive sublimation process or perhaps additional heating from some internal source or something else we haven't considered. Most scientists attribute this to the exceptional CO2 dominance. Dry ice simply becomes active at greater distances and lower temperatures than water ice does. Problem solved. But Avi Loeb, never one to leave a stone unturned, has asked a different question. Does Three-Eye Atlas generate its own light? This is speculation, clearly and explicitly speculation, but the question is worth understanding. If an object were powered by some internal energy source, whether radioactive decay, residual heat from formation, or something more exotic, it might glow and outgas even without significant solar heating. The mainstream scientific community finds no evidence for self-luminosity. The brightness spectrum and behavior of Three-Eye Atlas are entirely consistent with solar heating, driving sublimation of extremely volatile ices. Occam's razor applies the simplest explanation that fits the data is preferred. But the question illustrates something important about scientific inquiry. We should ask even unlikely questions, if only to test them rigorously and either confirm or rule them out. That's how science advances, not by assuming we already understand everything, but by challenging our assumptions. For now, the chemistry of Three-Eye Atlas tells a clear story. This is a comet formed in extreme cold in a planetary system with a very different chemical composition than our own billions of years ago. It has traveled through the galaxy for longer than Earth has existed, preserving its ancient ice in the deep freeze of interstellar space. And now, for a few brief months, we have the privilege of examining that ice as sunlight awakens it, releasing gases that last saw warmth when the universe was young. The chemical analysis continues. More observations are being made. More data is accumulating. But already, Three-Eye Atlas has taught us something profound. The ingredients that make comets and perhaps planets and perhaps life vary dramatically from one star system to another. If we want to understand how common life might be in the galaxy, we need to understand how common these ingredients are. How many variations exist? How different can the chemistry of planet-forming regions become? Every interstellar comet is a data point in answering those questions. And Three-Eye Atlas is one of the most valuable data points we've ever received. But before we explore what these findings mean for the search for life, we need to understand one more critical piece of context. How old is this object? When did it form? What was the universe like when Three-Eye Atlas was born? The answers are staggering. Close your eyes and imagine Earth's entire history compressed into a single year. January 1st represents the planet's formation 4.5 billion years ago. The first life appears in early March. Dinosaurs rule the Earth in mid-December and go extinct on December 26th. All of human civilization, from the first cities to the present day, occupies the last few minutes before midnight on December 31st. Now imagine something that existed before January 1st. Something that formed before Earth's year even began. Something that was already ancient when our planet was nothing but a cloud of dust and gas orbiting a newborn sun. That's Three-Eye Atlas. When astronomers analyzed the comet's trajectory, velocity, and kinematics, they could deduce certain properties about its galactic orbit. Remember that high perpendicular velocity, that 18.5 kilometers per second motion upward through the galactic plane. That velocity component is characteristic of stellar populations with significant age. Stars in the Milky Way can be divided into several populations based on their orbits and compositions. The thin disk contains young stars following relatively circular orbits close to the galactic plane. Stars like our Sun. The thick disk contains older stars on more eccentric and tilted orbit stars that oscillate up and down through the plane as they circle the galactic center. Objects associated with thick disk stars are on average significantly older than those associated with thin disk stars. They formed when the galaxy was younger, when stellar chemistry was different, when the metal content of gas clouds was lower. In July 2025, Matthew Hopkins and collaborators published a study analyzing 3I Atlas's kinematics and inferring its likely age based on typical thick disk populations. Their conclusion stated with 68% confidence 3I Atlas is between 7.6 and 14 billion years old. Let's put these numbers in context. Earth is 4.5 billion years old. The oldest rocks on our planet's surface date back about 4 billion years, preserved through extraordinary geological luck. The oldest evidence of life chemical signatures in ancient rock formations reaches back roughly 3.5 billion years. The Sun is 4.6 billion years old. It formed from a collapsing molecular cloud that had been enriched with heavy elements from previous generations of stars. Third-generation material in astronomical terms. 3I Atlas may be 7.6 to 14 billion years old. Let's take the midpoint estimate, roughly 10 billion years. That means 3I Atlas formed when the universe was only 3.7 billion years old. The universe is currently 13.8 billion years old, so 3I Atlas has witnessed approximately 72% of all cosmic history since the Big Bang. When this comet coalesced from ice and dust in the outer regions of its birth system, there was no Earth, no Sun, no solar system at all. The cloud of gas and dust that would eventually become our solar system was still scattered across a much larger volume of space, mixed with material from other future stellar systems warmed by different suns. Billions of years passed. 3I Atlas orbited its parent star, frozen and dormant in the outer darkness. Then something happened, perhaps a gravitational perturbation from a passing star, perhaps interactions during a close encounter with another system. Perhaps the chaotic dynamics of multiple planets, and it was ejected, cast out from the only system it had known, sent tumbling into the vast emptiness between stars. And it traveled. For billions more years it traveled through interstellar space. The distances are incomprehensible. Even at 3I Atlas's tremendous speed of 60+ kilometers per second, it would take tens of thousands of years to traverse a single light year. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. At 60 kilometers west, that journey would require roughly 21,000 years. And 3I Atlas has been traveling not for thousands of years, but for billions. It has crossed distances measured not in light-years, but in kiloparsecs, thousands of light-years. It has orbited the galactic center multiple times, riding the grand carousel of stars that constitutes the Milky Way's disk. Throughout this journey, it remained frozen. In the near absolute zero cold of interstellar space, temperatures hover just a few degrees above the cosmic microwave background. At these temperatures, molecules barely move. Chemical reactions essentially stop. Ice remains ice, preserved perfectly unchanging. 3I Atlas is a time capsule. The ice that forms its nucleus contains molecules that have been frozen solid for potentially 10 billion years. Those molecules were part of the protoplanetary disk around a star that may no longer exist. Stars like the Sun live for about 10 billion years, after which they evolve into red giants and eventually shed their outer layers as planetary nebula. The parent star of 3I Atlas might be gone. Died, exploded, transformed into a white dwarf cinder, slowly cooling in some distant corner of the galaxy. We may never identify which star system created this comet because that system may have been dispersed billions of years ago, yet the comet remains. A survivor, a messenger from a stellar system that may exist now only in the form of scattered atoms floating between the stars. This is why 3I Atlas is terrifying, not because it poses danger, but because it confronts us with the immensity of cosmic time. We live such brief lives. Human civilization has existed for perhaps 10,000 years. Anatomically modern humans have existed for perhaps 300,000 years. Our entire species is a geological eye blink, and here comes this fragment of ice, older than our world, carrying information from an era when the universe was fundamentally different. Younger, hotter, with fewer heavy elements, with different structures forming in different places. 3I Atlas is a physical connection to deep time, to a past so distant that Earth literally didn't exist.
And yet here it is in our sky, glowing softly as ancient ice is sublimated in sunlight that must seem impossibly bright and warm after billions of years in the frozen dark. When we observe 3I Atlas, we're looking at something that has witnessed eons we can barely comprehend. It has seen the galaxy evolve. It has passed by countless stars, sailed through nebulae, possibly witnessed supernovae from relatively close range. It has been a silent passenger on one of the longest voyages imaginable. And now, by purest chance, its wandering path has intersected ours. We exist in the same place at the same time for a few months, long enough for us to point our telescopes at it, analyze its light measure, its chemistry, calculate its trajectory, and then it will leave. It will continue its journey through the galaxy, moving away from us at 60 kilometers per second, receding back into the darkness. In a few decades, it will be beyond the orbit of Pluto, in a few centuries beyond the Oort cloud, in a few millennia approaching another star system, perhaps to be observed by someone, something else. Or perhaps it will travel for another billion years without ever again passing close to a star. Perhaps it will ride the galactic disk until the sun itself dies, until Earth is a cooling cinder, until our entire solar system is transformed beyond recognition. The universe is patient. 3I Atlas has all the time in the world, literally. It has already proven its endurance. But for us, for humanity, this moment is fleeting. We have one chance to study this ancient visitor, one opportunity to learn what it can teach us about the history of the galaxy, the diversity of planetary systems, the preservation of materials over cosmic timescales. And so the world's astronomers have mobilized every resource available. Because when something 10 billion years old passes through your neighborhood, you pay attention. You watch, you measure, you learn. And you remember that in the grand sweep of cosmic time, you and this ancient comet are both temporary visitors to this particular moment of the universe's evolution. The difference is the comet has seen so much more. In the summer and fall of 2025, something remarkable unfolded across planet Earth. From Hawaii to Chile, from Arizona to the Canary Islands, from space-based observatories circling our world, to probes orbiting Mars, humanity turned its collective gaze toward a single point of light moving through our solar system. It was one of the most coordinated observational campaigns in astronomical history, and it had to be because the target would only be visible for a limited time. Let's understand the challenge. When 3I Atlas was discovered on July 1, 2025, it was approaching the inner solar system from the direction of the constellation Puppies. Its trajectory would carry it through perihelion on October 29th, after which it would emerge on the other side of the Sun and begin its exit from our solar system, passing through the constellations, Virgo and Leo, before fading from view. But here's the problem. From approximately mid-October through early November 2025, 3I Atlas would be positioned nearly in line with the Sun from Earth's perspective.
During this period, it would be crossing the sky with the sun visible only during daylight, lost in the solar glare. Ground-based telescopes couldn't observe it. Even most space telescopes had to be careful pointing too close to the sun, risks damaging sensitive instruments. This meant the period around perihelion, when the comet would be most active, outgassing, most vigorously, potentially revealing the most about its composition, would largely be hidden from our view. Astronomers had a window before perihelion and a window after. The weeks before and after October 29th would be critical. The campaign began immediately after discovery. Within days of the announcement from the Minor Planet Center, observing proposals were submitted to every major telescope facility on Earth and in space. The Hubble Space Telescope was one of the first to respond. On July 21, 2025, Hubble captured the now iconic image of 3I Atlas showing its teardrop-shaped coma. The background stars appeared as streaks because Hubble was tracking the comet's rapid motion, a beautiful visual reminder of the extraordinary speeds involved. But Hubble's contribution went beyond pretty pictures. By imaging the comet multiple times with precise positioning, astronomers could measure the size of the coma track changes in brightness and crucially place upper and lower bounds on the size of the nucleus itself. Each observation added another data point to the growing understanding of this interstellar visitor. The James Webb Space Telescope, humanity's most powerful infrared observatory, observed 3I Atlas on August 6, 2025. JWST's near-infrared spectrograph dissected the light from the comet, revealing the molecular fingerprints of carbon dioxide, water vapor, and other compounds. This single observation provided more chemical information than had been obtained for either Oumuamua or 2I Borisov, a testament both to JWST's capabilities and to the advance warning of 3I Atlas's arrival. NASA's Neil Gehrels Swift Observatory, originally designed to detect gamma-ray bursts from distant cosmic catastrophes, turned its ultraviolet telescope toward the comet in July and August 2025. Swift's UV sensitivity allowed it to detect the faint glow of hydroxyl molecules, water that had been broken apart by solar radiation surrounding the nucleus. These observations confirmed water vapor was present despite the CO2 dominance, and tracked how the outgassing evolved as the comet approached the sun.
Ground-based observatories joined the effort. The Nordic Optical Telescope confirmed active outgassing. The Lowell Discovery Telescope in Arizona tracked the comet's brightness. The Canada-France-Hawaii Telescope on Mauna Kea measured its spectrum. Amateur astronomers with telescopes ranging from 8 inches to 16 inches in aperture contributed observations of position and brightness. By late September 2025, as 3I Atlas approached perihelion, it was becoming increasingly difficult to observe from Earth. The solar elongation, the angle between the sun and the object in the sky, was shrinking. The comet was heading behind the sun from our perspective, but there were other vantage points, other observers. On October 3, 2025, 3I Atlas passed within 30 million kilometers of Mars, its closest approach to any planet during its solar system transit. This represented an extraordinary opportunity. Several spacecraft were orbiting Mars, equipped with cameras and spectrometers designed for planetary observation. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express spacecraft were both positioned to potentially observe the comet. The challenge was significant. Their instruments were designed to image the bright surface of Mars from just hundreds to thousands of kilometers away. Now they would be attempting to photograph a faint, distant comet tens of millions of kilometers away. Between October 1st and 7th, 2025, both spacecraft turned their attention from Mars to the void beyond. The color and stereo surface imaging system, CASIS, aboard the Trace Gas Orbiter captured a series of images on October 3rd, when the comet was approximately 32 million kilometers from the spacecraft. The resulting images showed 3I Atlas as a slightly fuzzy white dot moving against the star field.
Not the most detailed observation ever obtained, but significant nonetheless, these were among the closest direct observations of the comet during the critical perihelion period. The fact that these spacecraft could observe the comet at all, despite their instruments being optimized for completely different targets, demonstrated the ingenuity and flexibility of mission teams responding to an unexpected opportunity. Meanwhile, other space-based assets contributed what they could. The GOES-19 weather satellite, primarily designed to monitor Earth's weather patterns, has the capability to detect objects down to apparent magnitude. 12. Between October 18th and 24th, 2025, GOES-19 tracked 3I Atlas, providing position measurements even as the comet became increasingly difficult for other observatories to follow. The Solar and Heliospheric Observatory SOHO, stationed at a gravitationally stable point between Earth and the Sun, observed the comet with its coronagraph instruments.
And the polarimeter, to unify the corona and heliosphere Punch satellite constellation, captured images showing the comet against the background of the solar corona. Then came perihelion. October 29, 2025, at 11:15 UTC, plus or minus 1 minute, the moment of closest approach to the Sun. At that instant, 3I Atlas was 203 million kilometers from our star position between the orbits of Earth and Mars, moving at 68 kilometers per second. Solar heating was at maximum intensity, approximately 770 watts per square meter of the comet's surface, like being under dozens of heat lamps simultaneously. And Earth couldn't see it. The comet was behind the Sun, hidden in the glare, invisible. This was the acid test that Avi Loeb referenced in his writings. If 3I Atlas was a fragile natural comet held together by weak forces, the intense heating might cause it to break apart, fragmenting into multiple pieces that would then evaporate more rapidly due to their increased surface area.
Or it might survive intact, its internal structures strong enough to withstand the thermal stress. We wouldn't know immediately. We'd have to wait for the comet to emerge from behind the Sun and become observable again. By mid-November 2025, 3I Atlas should be visible again in the pre-dawn sky from Earth, low on the eastern horizon before sunrise. At that point, it will be receding from the Sun, gradually diminishing in brightness as the outgassing decreases and the comet returns to dormancy. ESA's JUICE spacecraft, currently on its multi-year journey to Jupiter, is scheduled to observe the comet in November 2025. Although JUICE will be farther from 3I Atlas than the Mars orbiters were, it will catch the comet just after perihelion, when activity should still be strong. This provides a valuable post-perihelion data point to compare with pre-perihelion observations. In March 2026, NASA's Juno spacecraft orbiting Jupiter will have an opportunity to observe 3I Atlas when it passes within 54 million kilometers of the giant planet. By then, the comet will be cooling again, returning to its frozen state. Juno's instruments could potentially detect radio emissions if any existed, though none are expected from a natural comet. Throughout December 2025 and into early 2026, ground-based observatories will continue tracking 3I Atlas as it fades. The comet's apparent magnitude will drop below 12, requiring larger telescopes and longer exposures. Eventually, it will become too faint even for the largest instruments to vanishing back into the darkness from which it emerged. But the data will remain. Hundreds of observations from dozens of instruments, each adding a piece to the puzzle. Spectra showing composition, images revealing structure, measurements tracking how brightness varied with distance from the Sun. This collective effort represents humanity at its best. Researchers from different countries, different institutions, different backgrounds, all collaborating to study a phenomenon that transcends borders and politics. The comet belongs to no nation. It belongs to the cosmos. And our response to it, this worldwide vigil, demonstrates what we can accomplish when we work together toward a common goal. The observations continue even now. Even as you listen to this, somewhere on Earth or in space, an astronomer or a spacecraft is gathering light from 3I Atlas, preserving information that will be analyzed for years to come. Because this is how we learn. This is how science advances, not through speculation or assumption, but through careful, patient observation, through gathering data and testing hypotheses, through building a foundation of evidence upon which understanding can be constructed. And the evidence we've gathered about 3I Atlas has revealed something undeniable. This object is extraordinary, not just interesting, not just unusual. Extraordinary in ways that challenge some of our assumptions about comets and their behavior. Which brings us to the central question: the anomaly at the heart of this story. What about 3I Atlas doesn't quite make sense? Science progresses by identifying patterns, building models, and then testing those models against new observations. When the observations match the predictions, our confidence in the model increases. When they don't match, when something unexpected appears, that's when science gets interesting. 3I Atlas presents several unexpected features. Individually, each can be explained. Together, they create a portrait of an object that pushes the boundaries of what we understand about comets. Let's examine what doesn't quite fit the standard picture. First, the activation distance. When 3I Atlas was discovered on July 1, 2025, it was already showing signs of cometary activity, of faint coma and possible tail, yet it was still quite far from the Sun. For a typical comet in our solar system, significant outgassing doesn't begin until it crosses roughly the orbit of Jupiter, about 5 astronomical units from the Sun, and activity really intensifies inside Mars's orbit at around 1.5 AU. 3I Atlas began showing activity much farther out than expected, even accounting for carbon dioxide ice, which sublimates at lower temperatures than water ice. Now, this can be explained by the extreme CO2 dominance, the 8-to-1 ratio of carbon dioxide to water. CO2 is simply more volatile than H2O, meaning it transitions from solid to gas at lower temperatures and greater distances from the Sun. If your comet is mostly dry ice with only a small amount of water ice mixed in, you'd expect early activation. So explained, but it's still unusual enough to note. Second, the brightness evolution. As comets approach the Sun, their brightness typically increases predictably based on 2 factors. They're getting closer to the Sun, so receiving more sunlight, and they're getting closer to Earth, so the light has less distance to travel before reaching our telescopes. Astronomers can predict comet brightness fairly accurately using these geometric factors, plus the comet's albedo, how reflective its surface is. 3I Atlas has been brighter than some early models predicted. Not dramatically so, but measurably. It's glowing more intensely than would be expected for an object of its estimated size at its distance from the Sun. Again, this can be explained. A higher than expected outgassing rate driven by the CO2 dominance would eject more dust into the coma. More dust reflects more sunlight. Brighter comet. And indeed, the observations show a substantial coma, confirming vigorous outgassing. So explained. But the comet is on the bright end of expectations, perhaps suggesting the outgassing is more efficient than typical. Third, the spectral peculiarities. Remember those metal abundance measurements. High nickel, low iron. This is unusual for comets in our solar system, though. Admittedly, we don't have a huge sample of interstellar comets for comparison. The question is, does this represent a genuine difference in formation conditions, or is it telling us something else? The mainstream explanation is that different star systems have different elemental abundances based on their galactic chemical evolution. The molecular cloud that collapsed to form 3I Atlas's parent star had a different composition than the cloud that formed our Sun. The nickel-to-iron ratio simply reflects that ancestral chemistry. This makes sense. It's consistent with everything we know about how stars and planets form. Different systems should have different compositions. That's part of why studying interstellar objects is so valuable. They reveal this diversity. So explained, but it does mean 3I Atlas came from a stellar environment chemically distinct from our own. Fourth, the timing and trajectory. We've discussed this already, but it's worth revisiting. The path 3I Atlas takes through our solar system brings it relatively close to Mars, Venus, and Jupiter, with perihelion occurring when Earth can't directly observe it. From a statistical standpoint, this isn't particularly suspicious. Any object passing through the inner solar system will necessarily encounter the planets that live here. They're the biggest gravitational features around. So close approaches are inevitable. The ecliptic plane constrains where planets can be, and objects passing through that plane will naturally have planetary encounters. The perihelion timing, hidden behind the Sun from Earth's perspective, is simply geometry. Earth happens to be on the opposite side of the Sun during late October. That's not designed. It's just where we are in our orbit. So explained by mundane celestial mechanics, but it does create an observational challenge, and for those inclined toward speculation, a certain coincidental quality to the timing. Now here's where things get more intriguing. These are the observations that even mainstream astronomers find genuinely puzzling beyond simple, "that's unusual but explainable." Question 1. Why has the nucleus survived for so long? If 3I Atlas is truly 7 to 14 billion years old, it has been exposed to cosmic rays, interstellar radiation, and occasional heating from distant starlight for billions of years. Comets are fragile objects, loosely bound aggregates of ice and dust. They can break apart spontaneously. They erode in the harsh environment of space.
How has this particular comet remained intact for such an extraordinary length of time? What protected it is its internal structure, somehow more robust than typical comets. Is the CO2-dominated composition more stable over geological timescales? We don't have a definitive answer. The most likely explanation involves the deep cold of interstellar space at temperatures just a few Kelvin above absolute zero. Sublimation stops almost entirely, and the ice remains frozen solid, preserving structural integrity. But that's an assumption, not a proven fact. Question 2. What was the ejection mechanism? Something expelled 3I Atlas from its birth system billions of years ago. What was it? A gravitational perturbation from a passing star, interactions with giant planets during the system's youth, a catastrophic event like a stellar companion going supernova. Each scenario has different implications for how common such ejections are, which affects our estimates of the interstellar object population density. If ejection is rare, the galaxy might contain fewer wandering comets than we think. If it's common, there could be trillions of objects like 3I Atlas slowly drifting between the stars. We don't know. We can model various scenarios, but without knowing which star system 3I Atlas came from, we can't determine what actually happened. Question 3. Can we trace it back to its origin? Given its current trajectory and velocity, can we calculate backward through billions of years of galactic motion to identify the star system where it formed? The answer is probably not. Galactic dynamics are complex. Stars move, the galaxy rotates, spiral arms migrate. Gravitational perturbations from passing stars and molecular clouds alter trajectories over millions and billions of years. After 7+ billion years of wandering, the uncertainties become too large. We can say it probably came from the thick disk population, but identifying a specific star is likely impossible. This is frustrating. If we could identify the parent system, we could learn so much. Is the star still alive? Does it have planets? What is its composition? How does it compare to our Sun? But 3I Atlas may keep that secret forever. And then there's the question that a small minority of researchers, most prominently Avi Loeb, have raised repeatedly. How can we be certain this is a natural object? Let's be very clear about the scientific consensus before we discuss this speculation.
The overwhelming majority of astronomers studying 3I Atlas see absolutely no evidence for artificial origin. Every observed characteristic can be explained by natural cometary processes. The trajectory is consistent with a gravitationally unbound object passing through the solar system. The spectrum matches sublimating ices. The morphology looks like a comet. NASA's official position is straightforward. It looks like a comet. But Loeb has asked a series of questions worth considering, not because they're likely to be true, but because they illustrate an important principle. How would we actually recognize an artificial interstellar object if one passed through our solar system? What signatures would betray its true nature? Radio transmissions, we're listening but hearing nothing. Anomalous acceleration. Oumuamua showed slight acceleration, but that was likely outgassing. Geometric regularity. We can't resolve 3I Atlas's shape well enough to judge. If an advanced civilization sent a probe through our solar system disguised as a comet, and this is pure speculation, understand how would we distinguish it from a natural object? The uncomfortable answer is we might not be able to with current observational capabilities. This doesn't mean 3I Atlas is artificial. It almost certainly isn't. But it does mean we should think carefully about detection methods, about what signs we're looking for, about how we'd recognize the genuinely anomalous if it appeared. Because here's the truth. 3 interstellar objects in 8 years represents a tiny biased sample. We're seeing the largest, brightest, closest examples. Smaller objects, dimmer objects, objects on trajectories that don't bring them close to the sun. We're missing all of those. The galaxy could be full of interstellar wanderers, full of ancient comets cast out from their birth systems billions of years ago, full of materials and chemistries we've never encountered. And we're only now developing the capability to detect them. Each one teaches us something. Each one challenges our understanding in some way. Each one reveals that the universe is more diverse, more surprising, more mysterious than our models suggest. 3I Atlas is strange, genuinely strange, not strange in ways that can't be explained. We can construct natural explanations for every observed feature, but strange in the sense of being at the extreme edge of what comets do. The oldest, the fastest, the most CO2 dominated, the longest traveled. It pushes boundaries, it raises questions, it makes us think harder about our assumptions. And that's exactly what science needs. Not confirmations of what we already believe, but challenges. Anomalies. Objects that don't quite fit the boxes we've built. Because those are the objects that teach us the most. So, what do we make of 3I Atlas? How do we interpret this strange visitor? What hypotheses can we construct that account for the evidence while remaining scientifically sound? Let's examine 3 possibilities, starting with the most mainstream and progressing toward the more speculative, and let's see which one, if any, truly fits the facts. The simplest explanation is usually the correct one. This principle, known as Occam's razor, doesn't mean that simple explanations are always right, but it does mean we should prefer explanations that don't multiply assumptions unnecessarily. So let's start with the hypothesis that requires the fewest special assumptions. 3I Atlas is a natural comet, unusual in its properties, but fully explainable by known physics and chemistry. Here's how that story unfolds. Somewhere between 7 and 14 billion years ago, a molecular cloud collapsed under its own gravity. This cloud, composed primarily of hydrogen and helium with traces of heavier elements synthesized by earlier generations of stars, began to fragment and condense. Regions of higher density attracted more material, growing larger, spinning faster, as conservation of angular momentum dictated. One of these collapsing regions became a protostar, the ancestor of some distant sun we'll never identify. Around this protostar, a disk of gas and dust formed, swirling in the same direction as the star's rotation. This is the protoplanetary disk, the cosmic nursery where worlds are born. Temperature gradients existed within this disk. Close to the protostar temperatures were high hundreds or even thousands of Kelvin. Only refractory materials, rocks, and metals could condense there. Farther out, temperatures dropped. Water ice could condense beyond the snow line, typically around 3 to 5 astronomical units, depending on the star's luminosity. But in the outermost reaches of the disk, where temperatures plunged just dozens of Kelvin above absolute zero, even more volatile materials could freeze solid. Carbon dioxide, carbon monoxide, methane, nitrogen. These ultravolatiles would coat dust grains, accumulate in the coldest regions, freeze into icy mixtures dominated by materials that would sublimate instantly in the warmer inner system. This is where 3I Atlas formed. In the deep cold, in the outer darkness of its protoplanetary disk, perhaps 50 or 100 astronomical units from its parent star where sunlight was faint and temperatures were frigid. The exact chemistry of this region depended on the specific elemental abundances in the original molecular cloud. If that cloud had unusual ratios of carbon, oxygen, nitrogen, and other elements, perhaps due to being enriched by particular types of supernova, the resulting ices would reflect those unusual ratios. An 8:1 CO2 to water ratio suggests a carbon-rich, oxygen-poor environment compared to our solar system's formation region. Or perhaps it suggests formation at such extreme cold that water preferentially remained in the gas phase while CO2 froze more efficiently. Multiple scenarios could produce this composition. Over millions of years, these icy grains collided and stuck together, growing from microscopic particles to pebbles, to boulders, to kilometer-sized objects. This is planetary accretion, the same process that built the planets we know, just occurring in a different chemical environment. The resulting comet, our Proto-3I Atlas, was a loosely bound aggregate of ice and dust, dominated by carbon dioxide laced with water ice, and organic compounds perhaps a few hundred meters to a few kilometers across. It orbited its parent star in the cold outer system, one of potentially billions of similar objects in an extended cloud, analogous to our solar system's Oort cloud. And there it remained, frozen, dark, unchanging. Billions of years passed. The parent star evolved. Perhaps planets formed closer in. Perhaps those planets migrated their gravitational interactions, reshaping the architecture of the system. Perhaps a companion star passed nearby, its gravity stirring the outer cloud of comets. Whatever the specific mechanism, something perturbed 3I Atlas, changed its orbit, sent it on a trajectory that would carry it away from its parent star, away from the system of its birth, out into interstellar space. This ejection process is not exotic. Our own solar system has almost certainly ejected millions or billions of objects over its 4.6 billion year lifetime. Jupiter is a particularly effective ejector. Its massive gravity can accelerate smaller objects to escape velocity with a single close encounter. Saturn, Uranus, and Neptune can do the same, though less efficiently. Multiply this process by the roughly 100 billion stars in the galaxy, each potentially ejecting comets during their planetary system's youth, and you get an enormous population of interstellar wanderers. Current estimates suggest there might be trillions of rogue comets drifting through the Milky Way. So 3I Atlas joined that population. It entered the galaxy as a free-floating object, no longer bound to any star, traveling at the velocity it inherited from its ejection, plus the orbital motion of its birth system around the galactic center. And it traveled. For billions of years, it traveled through the near absolute zero cold of interstellar space. No sunlight warmed it. The nearest stars were light years away, their radiation diluted to negligible intensity. Cosmic rays struck its surface occasionally, very slowly, processing the surface ices, but the interior remained pristine, frozen solid, chemically unchanged. The galactic environment is not entirely empty. The interstellar medium contains sparse gas, perhaps 1 atom per cubic centimeter on average, and dust grains.
Passing through denser molecular clouds would expose the comet to slightly more material. But for the most part, the 3I Atlas experienced true isolation, true cold, true darkness. It orbited the galactic center along with billions of other stars and objects riding the grand rotation of the Milky Way's disk. Its tilted orbit carried it up and down through the galactic plane, that high W velocity marking it as a thick disk member, an ancient wanderer following an ancient path. And then, purely by chance, its trajectory intersected our solar system. Given the size of the galaxy, roughly 100,000 light-years across, and the number of stars, roughly 100 billion, the probability of any specific comet passing through any specific star system is extraordinarily low. But given enough comets and enough time, these encounters inevitably occur. In June 2025, 3I Atlas crossed the heliopause, the boundary where the sun's influence begins to dominate over the interstellar medium. It entered the realm of our star's gravity, not bound to it moving far too fast for capture, but passing through its gravitational field, trajectory bent slightly by solar attraction. As it approached the inner solar system, sunlight began to warm its surface for the first time in billions of years. At first, the effect was minimal, but as the distance to the sun decreased, temperatures rose. Carbon dioxide ice with its low sublimation temperature began to vaporize. Gas escaped from the nucleus, carrying dust particles along with it. A coma formed. Sunlight reflected from this cloud of gas and dust, making the comet visible, a faint smudge brightening as it approached. The Atlas survey detected it. Astronomers around the world turned their instruments toward it, and we began to document its properties. Everything we've observed fits this natural origin story. The composition expected for formation in an extremely cold environment with unusual chemistry. The age consistent with thick disk kinematics. The trajectory, standard hyperbolic path for an interstellar object. The activation distance explained by CO2 dominance. The brightness consistent with vigorous sublimation driven by volatile ices. There are no features of 3I Atlas that require anything beyond natural physics and chemistry. No signs of artificial construction. No evidence of propulsion. No radio transmissions. No geometric regularities. Nothing that can't be explained by a comet formed billions of years ago in another star system, ejected during that system's evolution and now passing through ours. This is the hypothesis favored by approximately 90% of professional astronomers studying the object. It is the scientific mainstream. It is the explanation that requires the fewest assumptions and fits the data most completely. Does that mean it's certainly correct? Number science doesn't deal in certainties, only in probabilities and evidence. But the evidence overwhelmingly supports a natural origin. 3I Atlas is strange, but the universe is full of strange things. Extremes of age, speed, composition, and trajectory are to be expected when you're sampling from a population of trillions of objects formed under diverse conditions across the galaxy's 13 billion year history. The natural explanation is not just plausible, it's compelling. It's consistent with everything we know about planetary formation, cometary physics, and galactic dynamics. It makes testable predictions that have been confirmed by observations. It fits. And yet, there are still elements that push the edges of what we expect. Features that, while explainable, are at the extreme end of the distribution. Properties that make 3I Atlas unusual even among interstellar objects. Which leads us to the second hypothesis. Still natural. Still based on known physics, but exploring edge cases. Unusual scenarios. Rare events that might explain why 3I Atlas is not just different, but extremely different. What if something out of the ordinary happened during its formation or journey? What if its story includes a chapter we haven't yet considered? Most comets have unremarkable histories. They form, they orbit, they occasionally pass close to the sun and put on a show. They're shaped by gravity and sunlight and time, but their stories are variations on a common theme. But some comets, a tiny minority, experience events that transform them. Catastrophes, close encounters, cosmic accidents that leave permanent marks on their composition and trajectory.
Could 3I Atlas be one of these rare exceptions? Could its unusual properties reflect not just where it formed, but what happened to it afterward? Let's explore several edge case scenarios, each representing legitimate natural physics, but unusual circumstances that might explain why this comet is so extreme. Scenario 1. Witness to catastrophe. Imagine the planetary system where 3I Atlas formed. Now imagine something goes wrong. Perhaps the parent star had a massive companion, a red giant or supergiant orbiting at a distance of hundreds of astronomical units. Over billions of years, this companion evolved, expanded, and eventually exploded as a supernova. The explosion wouldn't have vaporized 3I Atlas directly. It was too far away, perhaps, orbiting in a distant cloud of comets, analogous to our Oort cloud. But the blast wave, expanding at thousands of kilometers per second, would have swept through that region, delivering a tremendous gravitational kick to every object it encountered. Some comets would have been driven inward toward the parent star. Others would have been accelerated to escape velocity and ejected from the system entirely. 3I Atlas might have been one of the latter, flung into interstellar space, not by gentle perturbations, but by the violent death of a star. This scenario could explain the extreme velocity. Supernova-assisted ejection could impart much higher speeds than planetary perturbations alone, resulting in the high eccentricity we observe. It could also explain the unusual chemistry. If 3I Atlas formed before the supernova, it would have inherited the pre-explosion chemical signature of its birth environment. But the supernova itself would have created new elements, heavy metals, synthesized in the explosion and scattered them through the system. The high nickel-low iron ratio might reflect contamination from supernova ejecta, a thin coating of stellar debris deposited on the comet's surface as the blast wave passed. This is speculation, but it's grounded in known astrophysics. Supernovae do disrupt planetary systems. They do synthesize heavy elements. They do eject material at high velocities. All the pieces fit. Scenario 2. The stellar close. Encounter. Stars are not stationary. They orbit the galactic center, and occasionally they pass close to one another. Imagine 3I Atlas already ejected from its birth system billions of years ago, wandering through the galaxy. Now imagine it passes within a few thousand astronomical units of another star, not close enough to be captured, but close enough to feel significant gravitational effects. The flyby would alter 3I Atlas's trajectory, changing its velocity and direction. If the encounter occurred at just the right geometry, it could boost the comet's speed, substantially adding energy that would be reflected in the extreme hyperbolic eccentricity we now observe. Multiple such encounters over billions of years could have repeatedly modified the comet's path, sending it on an odyssey through the galaxy far more complex than simple ballistic motion. Each close approach would leave its mark, gradually sculpting the trajectory until by chance it pointed toward our solar system. This scenario is less exotic than a supernova, but perhaps more likely. Stellar encounters are common on galactic timescales. Given 7+ billion years of travel, 3I Atlas could easily have experienced dozens or even hundreds of distant stellar flybys. Scenario 3. Orphaned during birth. What if 3I Atlas never completed its formation in a stable planetary system? What if it was ejected prematurely? Planetary formation is chaotic. Protoplanetary disks are turbulent, with material spiraling inward eddies forming and dissipating shock waves propagating through the gas. In this environment, small forming planetesimals can be flung outward by gravitational interactions with larger, faster forming bodies. If 3I Atlas was expelled during the earliest phases of its system's evolution, while the protoplanetary disk was still present, it might have carried away an unusual chemical signature. Perhaps it formed from material that had only partially processed, or from a localized eddy in the disk with anomalous composition. This early ejection hypothesis could explain why 3I Atlas's chemistry is so different. It never equilibrated with the rest of the forming system. It never underwent the same thermal processing as other objects. It's a snapshot of an earlier, more primitive stage of planetary formation. Moreover, early ejection would give the object more time, potentially the full 10 billion years or more, to wander the galaxy before encountering our solar system. Time for its kinematics to be shaped by countless subtle perturbations. Time to accumulate the extreme velocities we observe. Scenario 4, the stripped core. Here's a more exotic possibility. What if 3I Atlas was once much larger, and what we're seeing now is just the core? Imagine a comet originally tens of kilometers across with a layered structure, an ice-rich mantle surrounding a denser core. Over billions of years of exposure to cosmic rays, to faint starlight, to the sparse interstellar medium, the outer layers slowly erode. In our solar system, this process is slow enough to be negligible over millions of years, but over billions of years in interstellar space. Different story. The cumulative effect of cosmic ray bombardment can process surface ices, converting them to more volatile or non-volatile forms that then escape or become chemically altered. If the outer layers were water-dominated and the inner core was CO2-dominated due to different formation temperatures or chemical gradients within the original protoplanetary disk, then stripping away the outer layers would reveal a core with extreme CO2-H2O ratios. This stripped core model is speculative, but it's testable. If 3I Atlas shows signs of a resistant, perhaps rocky layer beneath the active sublimating ices that would support this scenario, if density measurements difficult to obtain but possible with precise trajectory tracking suggest a denser than typical composition that would be consistent with a core rather than a pristine comet. Scenario 5, galactic chemical gradient. Finally, consider the possibility that 3I Atlas's unusual chemistry simply reflects where in the galaxy it formed. The Milky Way is not chemically homogeneous. The inner regions closer to the galactic center have higher metallicity, more heavy elements, because they've been enriched by generations of massive stars that lived fast, died young as supernova, and scattered newly synthesized elements into the interstellar medium. The outer regions farther from the center have lower metallicity, fewer heavy elements, different ratios of carbon, oxygen, nitrogen, and other elements. If 3I Atlas formed in a region of the galaxy with unusual chemical abundances, perhaps in the outer halo or in a dwarf galaxy that was later absorbed by the Milky Way, its composition would reflect that environment. The nickel-to-iron ratio, the CO2 dominance, even subtle isotopic signatures might all point to an exotic birth location. This hypothesis is elegant because it requires no catastrophe, no unusual event, just formation in a different part of the galaxy with different baseline chemistry. The Milky Way is large and diverse. Not every star system inherits the same materials. Each of these scenarios is plausible. Each is grounded in real astrophysics. Each could explain some or all of 3I Atlas's unusual properties, and each represents the kind of edge case thinking that good science requires. When you encounter something strange, you don't just default to, "It's probably normal." You also ask, what rare but natural process could produce this, because rare events happen. Given a large enough sample, trillions of comets scattered across billions of years, even extremely unlikely events become inevitable. Somewhere a comet witnessed a supernova. Somewhere a comet passed near a dozen stars. Somewhere a forming planetesimal was ejected at just the wrong moment and has been wandering for 10 billion years. 3I Atlas might be one of these statistical outliers. Not impossible, not supernatural, just rare. The challenge is determining which scenario, if any, actually occurred. Without knowing the origin system, without being able to visit the comet directly, without centuries of detailed observations, we're limited to informed speculation. But here's what we can say. Even in these edge case scenarios, 3I Atlas remains a natural object, shaped by natural processes, explainable by known physics. There's nothing here that requires us to invoke anything beyond the physics and chemistry we already understand. Nothing, unless we're willing to consider one more hypothesis, one that most scientists reject, but that a small minority argues we should at least evaluate. The hypothesis that 3I Atlas might not be natural at all. Before we proceed, let's be absolutely clear. What follows is speculation, not established science. Not the consensus view, speculation proposed by a small minority of researchers, most prominently Avi Loeb of Harvard, that the mainstream astronomical community largely rejects. But it's speculation worth understanding, not because it's likely to be true, but because it raises important questions about how we would recognize something genuinely anomalous if it appeared in our sky. So let's examine the hypothesis. What if 3I Atlas is not entirely natural? What if it's artificial or partially artificial? What if it represents technology from another civilization? Loeb framed this question in a paper titled, "Is the Interstellar Object 3I Atlas Alien Technology?" His argument is not that 3I Atlas definitely is artificial, but rather that we should seriously consider the possibility and establish criteria for distinguishing natural from artificial objects. He writes, "The hypothesis in question is that the recent interstellar visitor to our solar system, 3I Atlas, is a technological artifact and furthermore has active intelligence. If this is the case, then two possibilities follow. First, that its intentions are entirely benign, and second, they are malign or somewhere in between." He continues, "The consequences, should the hypothesis turn out to be correct, could potentially be dire for humanity and would possibly require defensive measures." This is provocative language, deliberately so. Loeb is asking us to take the question seriously enough to develop detection methods and response protocols even if the probability is low. So let's think it through. What evidence might support an artificial origin? Evidence point 1. The trajectory. We've noted that 3I Atlas passes relatively close to Mars, Venus, and Jupiter, with perihelion occurring when Earth cannot observe it. Loeb suggests this could reflect deliberate trajectory design, a path chosen to visit multiple planets, while minimizing detection from the most technologically advanced world, ours. The mainstream response. This is simply geometry. Any object passing through the inner solar system will encounter planets. The ecliptic plane constrains possible paths. There's nothing about the trajectory that can't be explained by natural gravitational dynamics. Loeb's counter. But if you were sending a probe to study a planetary system, wouldn't you design a trajectory that passed by multiple worlds? The fact that this path looks like what an intelligently designed flyby might look like doesn't prove intelligence, but it also doesn't rule it out. Evidence. Point 2. The timing perihelion on October 29, 2025, 2 days before Halloween, hidden from Earth behind the sun. Loeb describes this as the acid test. If the object is going to do anything unusual, deploy probes, change trajectory, broadcast signals, perihelion would be the optimal time. Maximum solar energy available, maximum gravitational assist potential, and Earth is blind to whatever happens. The mainstream response. Perihelion timing is determined by when the object enters the solar system and its velocity. It's not designed, it's calculated. The Halloween proximity is pure coincidence. Humans project meaning onto random patterns. Loeb's counter. But it's still worth monitoring carefully. If unusual activity occurs around perihelion fragmentation that doesn't match natural breakup velocity, changes that can't be explained by outgassing deployment of smaller objects, that would be significant. Evidence point 3. The brightness anomaly. Remember that 3i Atlas is slightly brighter than early models predicted. Loeb asked in an essay, "Does 3i Atlas generate its own light?" He notes that if the object had any internal power source, whether conventional nuclear power, radioactive decay, or something more exotic, it might glow independently of reflected sunlight. This self-luminosity would make it appear brighter than expected for its size.
The mainstream response. The brightness is perfectly consistent with strong outgassing driven by CO2 sublimation. More gas and dust in the coma equals more reflected sunlight. No self-luminosity required. Loeb's counter: have we definitively ruled out self-luminosity? Have we conducted tests, spectrum analysis at wavelengths that would reveal internal heating, for instance, that conclusively demonstrate all the light is reflected solar radiation? Evidence. Point 4. The composition as camouflage. Here's where the speculation becomes more interesting. What if an artificial object were deliberately designed to mimic a comet? If you wanted to send a probe through another civilization's solar system without triggering alarm, you might engineer it to look natural. Coat it in ice, allow sublimation to create a coma, match the spectroscopic signature of expected volatiles. The result would be indistinguishable from a natural comet without close-up inspection or extremely detailed analysis. The mainstream response. This is unfalsifiable. Any evidence that 3i Atlas is natural can be dismissed as the disguise is too good. This isn't science, it's conspiracy thinking. Loeb's counter: unfalsifiable doesn't mean impossible, and the question remains, how would we recognize an intelligently disguised object? What tests would definitively distinguish natural from artificial evidence? Point 5. The silence. No radio signals have been detected from 3i Atlas, no laser communications, no evidence of any transmission whatsoever. For most scientists, this silence is dispositive. If it were artificial, we'd expect some sign of technology. The absence of any such sign strongly suggests it's natural, but Loeb points out that absence of evidence is not evidence of absence. An advanced probe might communicate using methods we can't detect: entangled quantum signals, gravitational wave modulation, neutrino beams. Or it might simply be in passive observation mode, not transmitting at all. Moreover, our own Voyager probes are roughly 10 meters across, including their antennas. If an alien civilization sent a similarly sized probe past their sun, we might not detect it until it was quite close, and even then it would appear as little more than a faint dot of reflected light. We're limited by our technology. We see what we're capable of seeing, and we interpret based on what we know. But the universe is under no obligation to make itself comprehensible to our current instruments. So where does this leave us? Is there any merit to the artificial hypothesis? Scientifically, the answer is probably not. The evidence supporting an artificial origin is thin to non-existent. Everything observed can be explained naturally. The trajectory, the composition, the brightness, the silence all fit the natural comet hypothesis perfectly well. The artificial hypothesis requires multiple unsupported assumptions: that interstellar civilizations exist, that they send probes, that one reached our solar system now that it's disguised as a comet, that it's using undetectable communication methods. Each assumption reduces the probability. Applying Bayesian reasoning, updating probabilities based on evidence, the artificial hypothesis becomes vanishingly unlikely. Not impossible, but highly improbable. And yet, Loeb's underlying point deserves consideration. How would we recognize an artificial interstellar object if one did visit? Oumuamua showed us how difficult this question is. Its unusual properties, elongated shape, slight acceleration, lack of coma, sparked intense debate. Was it a comet with unusually low outgassing? A hydrogen iceberg? A nitrogen ice shard from a Pluto-like world? Or something else,
The scientific consensus settled on natural explanations, but the controversy revealed how uncertain we become when faced with truly novel objects. With 3I Atlas, we're more confident it's natural because it behaves more like a conventional comet, but more like isn't certainly is. We're making probabilistic judgments based on incomplete data. If we want to genuinely address the question of artificial interstellar objects, we need to develop better detection criteria. What signatures would definitively indicate technology improve our observation capabilities? Larger telescopes, better spectrographs, more sensitive radio receivers. Consider multiple hypotheses simultaneously testing each against data without prejudice. Maintain intellectual humility. The universe has surprised us before. It will surprise us again.
For now, the overwhelming likelihood is that 3I Atlas is a natural comet. Ancient, unusual, fascinating, but natural. The speculation about artificial origin is just that speculation. Worth thinking about as a thought experiment. Worth using to sharpen our thinking about detection methods, but not worth elevating to equal status with well-supported natural explanations. Science requires skepticism, yes, but it also requires proportion. We weight hypotheses by their evidence, and the evidence overwhelmingly favors a natural origin for 3I Atlas. Still, the questions linger, and that's okay. Science thrives on questions, on mysteries that haven't been fully solved, on the tension between what we know and what we still wonder about. Which brings us to the deeper implications of this visitor. Whether natural or artificial, and it's almost certainly natural. What does 3I Atlas mean for our understanding of the universe? What does it tell us about our place in the cosmos? And what might it mean for our future? Let's step back from the details, the spectra, the trajectories, the hypotheses, and ask a bigger question. What does 3I Atlas teach us about the universe we inhabit? The implications ripple outward in multiple directions, each profound in its own way. Implication 1. We are not isolated. For most of human history, we imagined Earth as the center of everything. The stars were lights embedded in a celestial sphere. The planets wandered across the sky according to divine will. The universe was small, comprehensible, centered on us. Copernicus moved Earth from the center. Galileo showed us we orbited the sun, not the reverse. Hubble revealed that our galaxy is one among billions each, containing billions of stars separated by inconceivable distances. And yet, even with this cosmic humility, there remained a sense that our solar system was an island, isolated, self-contained. Nothing came from outside, nothing left and returned. We were alone in our corner of space. 3I Atlas shatters that illusion definitively. We are not isolated. Our solar system is embedded in a galaxy full of material, and that material moves. It flows between stars. Objects formed in other systems pass through ours. We share the galaxy with countless other planetary systems, and their cast-offs visit us regularly. This is profound. It means Earth exists not in isolation, but in a galactic ecosystem. We're downstream from other star systems. Material formed elsewhere reaches us. Chemistry from other stellar environments arrives in our neighborhood. And it raises an intriguing possibility. If solid objects can travel between stars, could they carry something else? Could they transport complex molecules? Perhaps even the precursors of life from one system to another. Implication 2. The ingredients for life are common. When NASA's Swift Observatory detected water vapor escaping from 3I Atlas, Dennis Bodowitz said, "When we detect water from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. Water is essential for life as we know it. It's the universal solvent, the medium in which biochemistry occurs. Earth's oceans are the cradle of terrestrial life. And here's a comet from another star system formed billions of years ago in conditions very different from those in our solar system carrying water.
not just carrying it, outgassing it, releasing it into space as the sun warms its ancient ice. This suggests that water is common in planetary systems, that the formation of icy bodies containing water happens not just here, but throughout the galaxy, that wherever you have a protoplanetary disk, wherever you have temperatures low enough for water to freeze, you get comet-like objects carrying this crucial molecule. The same appears true for carbon-based compounds. We've detected organic molecules in 2I Borisov. We've found complex organics in meteorites that fall to Earth. The chemistry of life carbon chains, amino acids, nucleotides exists in space, forming naturally in cold environments. If these ingredients are common, if they're delivered to planets by comets and asteroids, then the chemical prerequisites for life might exist on millions or billions of worlds across the galaxy. This doesn't mean life is common. The jump from chemistry to biology, from molecules to self-replicating systems, is profound and poorly understood. But it does mean the starting materials are available. The universe is chemically rich, full of the building blocks from which life could potentially emerge. Implication: 3-planetary system. Diversity. Every interstellar object tells us about a different stellar environment. Oumuamua was dry and rocky. 2I Borisov was Ko-rich. 3I Atlas is CO2-dominated with unusual metal ratios. 3 objects, 3 completely different chemical profiles. This diversity is scientifically valuable because it reveals how variable planet-forming conditions can be. The temperature gradient in a protoplanetary disk depends on the star's luminosity. The chemical abundances depend on what earlier generations of stars synthesized. The architecture, how many planets form, where they form, whether they migrate, varies dramatically from system to system. Each interstellar visitor is a snapshot of a different formation environment. By studying many such objects, we can map the range of possible chemistries, the spectrum of conditions under which planets and comets form. This has direct implications for the search for habitable worlds. If every planetary system is unique, if there's no single, normal template, then we need to be open to diverse possibilities. Life might emerge in environments very different from Earth. Biosignatures might take forms we haven't anticipated. The universe is more creative than we are, and that's both humbling and exciting. Implication: 4. The interstellar object. Population. Based on the detection rate 3 confirmed objects in 8 years, astronomers can estimate how many interstellar objects pass through the inner solar system annually. Current models suggest dozens to hundreds per year, with the vast majority going undetected because they're too small or too faint. Beyond Neptune in the outer solar system, there might be one interstellar object at any given time. Over millennia, millions have passed through. This population represents an enormous archive of galactic materials. Every stellar system contributes to it. Every ejected comet, every cast-off planetesimal becomes part of the interstellar mix, and that population intersects every star system. We receive objects from across the galaxy. Other systems receive our ejecta in return. There's a galactic-scale exchange of materials happening constantly, invisibly over billions of years. Some scientists have speculated that this exchange could in principle transport extremophile microorganisms between star systems, a process called panspermia. If life arose on one world, could it seed others via comet impacts? This is highly speculative and controversial, but the physical mechanism exists. Comets do travel between stars. Material from one biosphere could in theory reach another. Whether it actually happens is unknown, but 3I Atlas proves the highway exists.
Implication 5. We need better technology. We almost missed 3I Atlas. It was hidden against the galactic center starfields for weeks before detection. It was only found because it moved into a clearer region of sky and automated software flagged it. How many interstellar objects have we missed entirely? How many passed through while we weren't looking or were too faint for our surveys, or moved through regions we don't monitor frequently? The answer is probably thousands. We're currently capable of detecting objects larger than a few hundred meters if they pass relatively close to Earth and are actively outgassing. Smaller objects, dimmer objects, objects on different trajectories, we miss them all. To properly study the interstellar object population, we need larger surveys covering more sky more frequently, more sensitive detectors capable of spotting fainter objects, rapid response systems that can quickly redirect telescopes to study discoveries, spacecraft capable of intercepting interstellar visitors before they leave the inner solar system. That last point is particularly important. ESA's Comet Interceptor mission, scheduled to launch in 2029, will wait in space at a gravitationally stable point, ready to chase any suitable target that appears, whether a pristine Oort cloud comet or, if we're extraordinarily lucky, an interstellar visitor. Intercepting an interstellar object with a spacecraft would be transformative. We could measure its composition directly, map its surface, determine its internal structure, settle questions about age and origin that spectroscopy alone can't answer. The technology exists. We just need to commit the resources and wait for the right opportunity. Implication 6. The question of intelligence. Even if 3I Atlas is natural, and it almost certainly is, its passage raises important questions about how we search for extraterrestrial intelligence. If civilizations exist elsewhere in the galaxy, they might explore using small probes rather than massive starships. These probes could be comet-sized or smaller, indistinguishable from natural objects without close inspection. How would we recognize them? What tests would differentiate technology from geology? SETI traditionally focuses on radio signals, but a truly advanced civilization might use different methods: optical lasers, neutrino beams, gravitational wave modulation, or they might simply explore passively their probes, observing without transmitting. 3I Atlas, whether natural or not, should make us think harder about our search strategies.
Are we looking for the right signatures? Are we prepared to recognize something genuinely anomalous if it appears? The prudent approach is to continue studying interstellar objects, carefully applying multiple analysis techniques, remaining open to surprising findings while maintaining scientific rigor. Because here's the truth. If we ever do detect genuine evidence of extraterrestrial technology, it might come not from a radio signal, but from an unusual object passing through our solar system. Better to have thought about how we'd recognize such a thing in advance. These implications cascade outward, each raising new questions, each opening new avenues of research. 3I Atlas is not just a data point, it's a teacher. A reminder of how much we still don't understand about the cosmos. But perhaps the most profound implication is existential. It's about perspective, about how we see ourselves and our place in the universe. And that brings us to questions that aren't purely scientific. Questions that touch on philosophy, on meaning, on what it means to be human in a cosmos full of ancient wanderers. Science advances by answering questions, but every answer generates new questions. The more we learn, the more we realize how much remains unknown. 3I Atlas is no exception. Despite intensive study, despite observations from the world's best telescopes, despite hundreds of hours of analysis, fundamental questions remain unanswered. Let's catalog what we still don't know. Question 1. How big is it really? We have estimates somewhere between 440 meters and 5.6 kilometers across, but that's a wide range. The difficulty lies in separating the faint nucleus from the bright coma surrounding it. From Earth's distance, the two blend together. Why does size matter? Because size determines mass, and mass determines structural properties. A larger nucleus can survive more. Thermal stress can retain volatiles, better can potentially last longer during repeated solar encounters. If 3I Atlas is toward the small end of the size range, it might be mostly pristine ice, largely unaltered since formation. If it's toward the large end, it might have a more complex internal structure, with different layers reflecting different formation epochs. We won't know precisely without closer observations either, a spacecraft flyby or continued ground-based observations that better constrain the nucleus's light contribution versus the coma's. Question 2. What is its rotation? State, does 3I Atlas spin? If so, how fast and around which axis rotation affects how a comet outgasses? A rapidly rotating nucleus can eject material more efficiently due to centrifugal effects. A slowly rotating nucleus might develop hot spots that dominate sublimation. Measuring rotation requires detecting periodic brightness variations as different surface areas face the sun. With 3I Atlas, the coma complicates this. The coma's brightness changes can mask the nucleus's rotation signature. But knowing the rotation state would help us understand the comet's mechanical properties and how torques from outgassing might be altering its spin over time. Question 3. Did it survive? Perihelion intact. We won't know until November 2025 when 3I Atlas re-emerges from behind the sun and becomes observable again. If it fragmented during perihelion passage, we'll see multiple pieces separating each, developing its own coma. This would tell us the internal structure was weak, held together by minimal tensile strength. If it survived intact, that suggests robust internal bonding either through sintering ice grains fusing together over billions of years, or a matrix of stronger material, or simply a lucky trajectory that avoided the most extreme thermal stress. Fragmentation is common among comets. Seeing whether 3I Atlas broke apart will provide crucial data about the longevity and resilience of ancient interstellar objects. Question 4. Can we trace it to its origin star? Given its current trajectory and velocity, can we calculate backward through billions of years to identify where it came from? The short answer is probably not with precision. After 714 billion years, small uncertainties in trajectory accumulate into enormous positional uncertainties. Gravitational perturbations from encounters with stars, molecular clouds, and even dark matter structures introduce chaotic elements that make long-term trajectories unpredictable. We can constrain possibilities. It likely came from the thick disk population from a region of the galaxy with specific chemical properties, but identifying the actual parent star is beyond our current capabilities. Future advances in galactic dynamics modeling combined with better understanding of stellar motions over time might narrow the possibilities, but the odds of definitive identification are low. Question 5. How many more are coming? 3I Atlas is the third confirmed interstellar object in 8 years. Will detections continue at this rate, accelerate as surveys improve? Or was this a statistical cluster with longer gaps ahead? Estimating the interstellar object population density is crucial for planning future missions and understanding galactic ecology. If objects like 3I Atlas are common, we can expect regular opportunities for study. If they're rare, each detection becomes more precious. Current models suggest we should detect several per decade with existing surveys and potentially dozens per year with next-generation facilities like the Vera Rubin Observatory, which will begin operations soon. But models are only as good as their assumptions. The true population density remains uncertain. Question 6. What will November tell us? When 3I Atlas becomes observable again after perihelion, what will we see? Will it be brighter than before, having been activated to maximum outgassing, or dimmer? Having lost significant volatile mass during perihelion passage, will it show continued activity, or will it be shutting down as it recedes from the sun and returns to deep freeze? The post-perihelion observations scheduled for mid-November through December will answer these questions. They'll reveal whether the heating fundamentally changed the comet's structure or whether it emerged essentially unchanged from its brush with solar fire.
Question 7. What about the next one? When will the fourth interstellar object be discovered? What will its properties be? Will it fit the patterns we're starting to see, or will it shatter them entirely? History suggests each interstellar visitor is unique. Oumuamua was rocky and elongated. 2I Borisov was a typical-looking comet. 3I Atlas is CO2 dominant and extraordinarily old. The fourth might be something else entirely: a metallic asteroid, a nitrogen ice fragment, a carbon-rich body unlike anything in our solar system. We're sampling from a population we barely understand. Each new detection refines our models, but also reveals how much diversity exists. The wait for the next interstellar visitor is part of the journey, and when it comes, we'll be better prepared than we were for Oumuamua, better equipped than we were for 2I Borisov, more ready than we were for 3I Atlas. These unanswered questions aren't failures of science. They're invitations, challenges, opportunities for future discoveries. Some will be answered in the coming months as observations continue. Others might take years or decades, requiring new instruments and new techniques. And some may remain mysteries indefinitely, simply because the information needed is lost to time or distance. But that's okay. Science doesn't require us to know everything. It requires us to keep asking, keep observing, keep learning. 3I Atlas has taught us an enormous amount already. What it teaches us next will depend on what questions we're clever enough to ask and what tools we're ambitious enough to build. The universe is full of mysteries. This ancient visitor is just one, but it's a mystery that arrived in our sky, accessible to our telescopes, available for our study, and that makes it precious beyond measure. When news of 3I Atlas first broke, the public reaction followed a predictable pattern. Media headlines ranged from sober scientific reporting to sensationalist speculation. Interstellar comet passing through solar system competed with scientist baffled by mysterious object from another star, and inevitably, could this be an alien probe? This disparity between careful scientific analysis and breathless speculation highlights an ongoing tension in how we communicate about space discoveries, especially ones as unusual as interstellar visitors. Let's examine how the scientific community has responded to 3I Atlas and what this tells us about the process of science itself. The overwhelming majority of professional astronomers studying 3I Atlas have concluded it's a natural comet with unusual but explainable properties. This conclusion is based on spectroscopic evidence showing composition consistent with icy volatiles, morphological observations revealing coma and tail structures, typical of comets, brightness variations matching expected sublimation-driven outgassing, trajectory calculations showing standard hyperbolic path with no anomalous accelerations, complete absence of any technological signatures, radio signals, geometric regularities, etc. Papers published in peer-reviewed journals have focused on characterizing the object's chemistry, constraining its physical properties, and comparing it to other comets, both interstellar and solar system bound. The tone is measured. Excited, yes, this is a remarkable object, worthy of intense study, but not sensational. The consensus is that 3I Atlas, while extreme in some properties, fits within the framework of natural cometary physics. Jacqueline McCleary of Northeastern University captured this perspective. Interstellar objects are the only things that we've ever gotten physical observations for within our solar system that originated outside our solar system. Each one is a window into what the pristine material is for other solar systems, which is precious. This is the scientific mainstream fascination tempered with rigor wonder, balanced with evidence. Then there's Avi Loeb, Harvard professor, former chair of the astronomy department, prolific researcher with hundreds of peer-reviewed papers, and the most prominent voice arguing, we should seriously consider non-natural explanations for interstellar objects.
Loeb's position on 3i Atlas as with Oumuamua before it is nuanced but provocative. He doesn't claim the object is definitely artificial. He argues we should evaluate that possibility rigorously rather than dismissing it out of hand.
In his paper, Is the Interstellar Object 3i Atlas Alien Technology? Loeb writes, the consequences should the hypothesis turn out to be correct could potentially be dire for humanity and would possibly require defensive measures. He's essentially applying a precautionary principle. If there's even a small chance this represents technology, we should investigate thoroughly because the implications are profound. Many of Loeb's colleagues find this approach frustrating. They argue, extraordinary claims require extraordinary evidence, and there is zero evidence for artificial origin. Invoking technology when natural explanations suffice violates Occam's razor speculating publicly about alien artifacts before exhausting natural hypotheses damages scientific credibility. The media amplifies these speculations, misleading the public about scientific consensus. These criticisms have merit. The artificial hypothesis for 3i Atlas is unsupported by current evidence. Promoting it prominently risks confusing public understanding, but Loeb's defenders counter that science advances by considering multiple hypotheses, even unlikely ones. We need clear criteria for recognizing artificial objects if they ever do appear. Public engagement, even through speculative questions, increases interest in astronomy. Being wrong while exploring interesting ideas is better than not exploring them at all. There's truth on both sides. The tension between them reflects a deeper question. How conservative should science be? When do we cross the line from healthy skepticism to closed-mindedness? Part of the problem lies in how media covers these stories. A headline reading, "Astronomers conclude interstellar comet is natural object with unusual chemistry," doesn't get clicks. Harvard scientist alien probe may be visiting solar system does. This creates a distortion. The majority scientific view that 3i Atlas is natural gets less attention than the minority speculative view. The public receives a skewed impression that the artificial hypothesis is more viable than it actually is. Responsible science communication requires walking a tightrope. Be honest about uncertainties without amplifying fringe theories. Generate excitement without sensationalizing. Acknowledge speculation while clearly labeling it as such. This documentary has attempted that balance. We've presented 3 hypotheses with appropriate weighting: 60% to natural explanation, 25% to edge case natural scenarios, 15% to bold speculation. And we've been clear about which is which. That's the standard we should hold all science communication to. The 3i Atlas response demonstrates that science is not a monolithic entity. It's a process messy and human, involving disagreement and debate. Scientists argue they have different thresholds for evidence. They prioritize different values, some emphasizing caution and rigor, others emphasizing creativity and exploration. This isn't a weakness, it's a feature. Scientific progress depends on this tension between conservative and bold thinking. You need both researchers who carefully analyze existing frameworks and researchers who challenge those frameworks with new ideas. The key is that these debates happen within a system of checks and balances. Hypotheses must be testable. Claims must be supported by evidence. Peer review filters out the most egregious errors. Replication confirms or refutes findings. 3i Atlas has been subjected to this system. Multiple independent observations confirm its basic properties. Multiple research teams have analyzed the data. The conclusions are convergent, natural comet, unusual chemistry, no signs of technology. That's the current scientific consensus. It could change if new evidence emerges. That's what makes it science rather than dogma. But it would require compelling evidence to overturn.
For now, the most reasonable position is 3I Atlas is a fascinating natural object worthy of continued study. The speculation about artificial origin, while intellectually interesting, is not supported by current observations. Science works, not perfectly and not instantly, but reliably over time. The 3I Atlas investigation demonstrates this beautifully. We're living through a pivotal moment in human history. Future generations will look back on the early 21st century as the era when humanity first became aware of the interstellar visitors passing through our solar system. Before 2017, these objects were theoretical. After Oumuamua, they became real. With 2I Borisov and now 3I Atlas, they're becoming routine, not common, but no longer shocking. This shift in perspective is profound. Let's explore what the legacy of 3I Atlas might be.
Legacy 1. The beginning of interstellar object science. In 2025, studying interstellar objects is a new field. We have 3 confirmed examples: limited observational windows and mostly remote sensing data. It's frontier science, full of uncertainties and debates. By 2050, this field will be mature. We'll have detected dozens or hundreds of interstellar visitors. We'll have developed standardized observation protocols. We might have successfully intercepted one with a spacecraft obtaining direct samples and close-up images. By 2100, we might have a comprehensive catalog of interstellar object types, chemistries, and trajectories. We'll understand the galactic population density, the ejection mechanisms, the preservation processes. Interstellar object science will be routine. 3I Atlas is one of the foundation stones of that future field. Every observation contributes to the permanent archive. Every paper analyzing its properties becomes part of the literature. Every lesson learned improves our readiness for the next visitor. Historians of science will reference 3I Atlas the way we now reference the first detection of an exoplanet or the first image of a black hole. It's a milestone, a before and after moment. Legacy 2. Technological development. Studying 3I Atlas has pushed technological boundaries. Getting useful data from Hubble, JWST Swift Mars orbiters, and ground-based telescopes required innovative techniques and rapid coordination. These capabilities will improve. The Vera Rubin Observatory, currently under construction, will revolutionize sky surveys with its massive field of view and sensitive detectors. It will find interstellar objects earlier, providing more warning time for follow-up observations. The Nancy Grace Roman Space Telescope, launching later this decade, will contribute infrared capabilities superior to anything currently available. ESA's Comet Interceptor will demonstrate rapid response spacecraft missions.
By the 2030s and 2040s, we'll have a network of space and ground-based assets specifically designed to detect and characterize interstellar visitors. We'll go from lucky discoveries to systematic monitoring, and eventually, perhaps by mid-century, we'll have the technology to send fast probes to intercept interstellar objects in the outer solar system, studying them up close before they vanish back into the void. 3I Atlas is teaching us what we need to build, what questions we need to answer, what capabilities we need to develop. It's a dress rehearsal for more ambitious future missions. Legacy 3. A shift in cosmic perspective. Throughout most of history, humans imagined the universe as static and separate. The heavens were unchanging, distinct from the changing Earth. Modern astronomy shattered that view. We learned the universe expands. Stars are born and die. Galaxies collide. Everything moves, everything changes, everything connects. But solar systems still felt isolated. Separate bubbles of planetary activity surrounded by vast, empty spaces. Interstellar objects complete the picture. Solar systems aren't isolated. They exchange material constantly. What forms in one system can visit another. The galaxy is a connected ecosystem, not a collection of islands. This perspective shift is subtle but important. It affects how we think about life's origins. If organic molecules and water travel between stars, panspermia life seeding across stellar distances becomes more plausible. Perhaps life arose once and spread. Perhaps Earth's biosphere has interstellar ancestors. It affects how we think about humanity's future. If we ever develop interstellar travel, we'll be following paths that natural objects have traveled for billions of years. The roots exist, we're learning to navigate them, and it affects our cosmic humility. Earth is not separate, not special, not isolated. We're embedded in a galaxy-wide process of material exchange that has been operating since the first stars formed. Tri-Atlas is a physical manifestation of that connection, a tangible reminder that we share the galaxy with other worlds, other histories, other stories. Legacy 4: Education and Inspiration. How many children are looking up at the night sky right now, knowing that somewhere out there, faint and receding, is a visitor from another star system? How many are inspired to study astronomy, physics, chemistry, engineering because of stories like 3i Atlas? The impact is impossible to quantify, but undeniably real. Space discoveries inspire. They capture imagination. They make abstract concepts tangible. A teacher can show students the Hubble image of 3i Atlas and say, "This object is older than Earth. It comes from another star, and we detected it, studied it, learned from it." That's powerful. It demonstrates what science can achieve. It shows that the universe, despite its vastness, is not beyond our ability to explore and understand. Some of those inspired students will become the scientists, engineers, and mission planners of the 2040s and 2050s. They'll design the missions that intercept the next generation of interstellar visitors. They'll answer questions we can't answer today. The legacy of 3i Atlas extends forward through generations. Legacy 5: Preparation. Finally, 3i Atlas is teaching us to be prepared for the next interstellar visitor, for unexpected discoveries, for objects that don't fit our categories. The astronomical community learned from Oumuamua's rapid transit. We missed most of the observation window because we weren't prepared. With 2i Borisov, we did better. With 3i Atlas, better still. Each experience improves our reflexes, our coordination, our ability to rapidly mobilize resources and focus attention where it's needed. This preparation extends beyond astronomy. If we ever do detect something genuinely anomalous, whether in the form of an interstellar object or a radio signal or something else, we'll need protocols, decision-making frameworks, international cooperation mechanisms. 3i Atlas is a dry run for that eventuality. It's teaching us how to respond collectively to cosmic phenomena, how to share data, how to build consensus, how to distinguish signal from noise. These are skills that will serve humanity well, regardless of what the universe sends our way next. The legacy of 3i Atlas isn't just scientific, it's cultural, educational, inspirational. It's about how we see ourselves and our place in the cosmos. This ancient visitor, formed when the universe was young, has traveled billions of years to reach us. It will be studied, remembered, and referenced for centuries to come. That's the legacy. Not just data and papers, but a shift in human consciousness, an expansion of our cosmic awareness. We are not alone in an empty universe. We're participants in a galactic story, billions of years old, still being written, still unfolding, and 3i Atlas is one sentence in that vast narrative. So we return to where we began, to the question that opened this exploration. Right now, something impossibly old is passing through our solar system, something that has been traveling through space since before Earth existed. 3i Atlas, the ancient wanderer, the cosmic messenger carrying information from a time when the universe was fundamentally different. Let's summarize what we know with certainty. 3i Atlas was discovered on July 1, 2025 by the Atlas Survey Telescope in Chile. It's the third confirmed interstellar object to pass through our solar system, following Oumuamua in 2017 and 2i Borisov in 2019. It has an orbital eccentricity of 6.137, the highest of any interstellar object detected, indicating it's moving far too fast to be captured by the Sun's gravity. At perihelion on October 29, 2025, it passed 203 million kilometers from the Sun between the orbits of Earth and Mars. Observations from Hubble JWST Swift and numerous other telescopes reveal it's a comet with extreme CO2 dominance, an 8-to-1 carbon dioxide to water ice ratio suggesting formation in the outermost reaches of a planetary system with chemistry different from our own. Its kinematics indicate it's 7 to 14 billion years old, making it potentially twice as old as Earth and the oldest comet ever observed. It has traveled through the galaxy for most of cosmic history, preserving ancient ice in the deep freeze of interstellar space. At its closest approach to Earth on December 19, 2025, it will be 267 million kilometers away, completely safe, no danger whatsoever. The scientific consensus, supported by overwhelming evidence, is that 3I Atlas is a natural comet. Unusual, extraordinary even, but natural. Every observed characteristic can be explained by known physics and chemistry without invoking anything exotic. That's what we know. What remains unknown? We don't know exactly how big it is, though estimates range from 440 meters to 5.6 kilometers. We don't know if it survived perihelion intact. We'll find out in November 2025 when it becomes observable again. We don't know which star system created it, and we'll probably never know with certainty. We don't know how many more interstellar visitors are heading our way or when the next one will arrive. And we don't know what 3I Atlas will look like when it re-emerges from behind the Sun. Will it still be actively outgassing? Will it have fragmented? Will it show unexpected changes? The observations continue. The story isn't finished, but here's what we can say about the terrifying truth. The real meaning of that word, terrifying, in our title. It's not terrifying because of danger. Earth is safe. The comet passes at a comfortable distance, poses no threat, will vanish back into space without affecting us. It's terrifying because of what it represents. Because of the timescales involved, because something formed 10 billion years ago when the universe was young and Earth didn't exist, has arrived in our sky for a brief moment before continuing its eternal journey. It's terrifying because it forces us to confront deep time, geological time, cosmic time, spans of duration so vast that human civilization, all of it from the first cities to the present day, is less than an eye blink. 3I Atlas existed before our world. It will exist after our world ends. It's a physical connection to a past so distant we can barely conceive of it, and to a future equally remote. That's terrifying in the most profound sense. Not scary, but awe-inducing, overwhelming. A reminder of our cosmic smallness and the universe's patient vastness. But it's also beautiful. Because we detected this ancient visitor, we studied it. We learned from it. Creatures who live for perhaps 80 years pointed telescopes at something 10 billion years old and extracted meaning from its light. That's the human story. Brief lives illuminating vast mysteries. Temporary beings comprehending eternal processes. We exist for a moment, but in that moment we reach out and touch the infinite. 3I Atlas is teaching us about chemistry and other star systems, about the age and structure of the galaxy, about how planetary formation varies across space and time, about the population of objects drifting between stars, about our own capabilities and limitations as observers. Every answer generates new questions. Every discovery reveals deeper mysteries. That's not frustration, that's the essence of science. The joy of perpetual exploration. So where does this leave us? With wonder, with questions, with the knowledge that our solar system receives visitors from across the galaxy, carrying messages written in ice and rock and ancient starlight. The universe is not empty. It's full of travelers, full of stories, full of materials that formed under conditions we can barely imagine, that have journeyed distances we can't truly comprehend, that arrive in our sky for reasons that are nothing more and nothing less than the working out of gravitational physics across billions of years.
This is the third interstellar visitor we've confirmed. There will be a fourth, a 10th, a 100th. Each will teach us something. Each will reveal another facet of the galaxy's incredible diversity. And perhaps someday, one will reveal something genuinely unprecedented, something that challenges our understanding in ways we can't anticipate, something that forces us to expand our categories and rebuild our theories. Will that visitor be natural or artificial? We can't know until it arrives.
But we'll be watching. We'll be ready. We'll apply the same rigorous analysis we've applied to 3I Atlas testing hypotheses, weighing evidence, following the data wherever it leads. Because that's what we do. That's who we are. A species that looks up, that wonders, that seeks to understand. 3I Atlas is receding now. Every second it moves 60 kilometers farther from the sun, 60 kilometers deeper into the darkness beyond. Soon it will pass Neptune's orbit, then the heliopause, then true interstellar space. And it will continue for millions more years, billions more years. Perhaps it will eventually pass by another star system, illuminated briefly by alien sunlight, observed by other beings asking the same questions we ask. Or perhaps it will drift for another 10 billion years without ever again feeling the warmth of a star. The universe is patient. Time is long. And 3I Atlas has all the time in the world. But we don't. Our window is closing. By February 2026, the comet will be too faint for most telescopes to track. It will fade into the background of distant stars, distinguishable only in archived images, remembered only in scientific papers and stories like this one. And then it will be gone. Not destroyed, just beyond our reach. Beyond our ability to study, back in the realm of the unknown. So pay attention now while you can. Look up if you have access to a large telescope. Think about what you're seeing: light reflecting off ice that formed when the universe was young. Photons that traveled millions of miles to reach your eyes, carrying information from impossibly far away. That's the gift 3I Atlas brings. Not danger, not threat, just information, just wonder. Just a reminder that we live in a universe stranger and more magnificent than we often remember. The terrifying truth is that the universe is old. So old that objects like this exist. So old that something can travel for 10 billion years and still be moving, still be coherent, still be recognizable as a comet when it finally encounters another star. And the beautiful truth is that we get to witness it. Brief as our lives are limited, as our perspective is, we can still point instruments at the sky and decode the messages written in ancient ice. That makes us part of the story. Temporary, yes, small, certainly, but present, aware, capable of wonder. 3I Atlas is leaving, but the questions it raises remain. When it formed 10 billion years ago in a star system we may never identify, long before Earth existed. Long before the sun ignited, was it already destined to pass through our solar system in 2025, or is the universe simply more crowded with ancient travelers than we ever imagined? And if this is the third we've found in 8 years, what else is out there moving through the darkness, carrying stories from across the galaxy? What's coming next? The universe waits patiently. The ancient travelers continue their journeys. And we brief, curious, persistent will be watching, always wondering, always reaching toward the infinite. Thank you for listening to this exploration of 3I Atlas and the mysteries it represents. If you enjoyed this deep dive into cosmic mysteries, consider subscribing for more long-form science documentaries. Share your thoughts and theories in the comments. And keep looking up. The next interstellar visitor could arrive at any moment. Clear skies and cosmic dreams.